Alrighty, so here we are with the 2-4 notes for pre-calc, and we're going to find some roots and zeros of polynomials through division. So we'll be doing long division again and synthetic division, if you remember back to Algebra 2. Alright, so the first thing we're going to do is long division. So in order to set this up, it is saying that you're going to divide x minus 2 into this trinomial and see what we can get. They do also say that they want the answer in what we call polynomial form and then also fraction form, and so we'll go through each of those, but ultimately that is not a huge issue. So first thing we're going to do is make our little fraction long division setup here. So inside the house goes this f of x, so 3x squared plus 7x, or the larger idea, and then the smaller one, x minus 2, goes out front. Remember that as you're doing this, you always want to make sure that you include each of the powers underneath your dividing bar here, and then also out here. It just really makes everything a lot easier, because otherwise you're going to end up kind of trying to subtract something that is not possible. You can only subtract like powers of terms. Alright, so first thing we need to do, and it's a little easier if you do it this way, just take this first piece and divide it into your first term. If you do that, you realize that 3x is what you need in order to get this done. And so we're going to put 3x in this column, noting that that's the x column. This would be the number column, and anything that's squared would have gone here. And then I'm going to multiply out. So I'm going to multiply 3x times x and get 3x squared, which is what we're hoping for. And then 3x times negative 2 and get negative 6x. Then we need to subtract them. And so when you subtract, notice that we are subtracting a negative in that second piece. So just be aware. The first column you subtract and you get 0, which is what we want. And then the second column is actually 7 minus negative 6. So that means 7 plus 6, which means that we'll have 13x. After that, we bring down our negative 20, and now we're trying to find what's going to multiply by x in order to get 13x. So you can always just divide out that x and realize that it's 13 that we would put in that next column. So 13 is going to go here, and then we'll multiply that by x to get 13x, and by negative 2 to get negative 26. Then we subtract these pieces. Again, notice that I put a subtraction here as well so that I don't forget that it is actually going to become plus 26. Alright, and then canceling this is 0, but then the next piece is going to result from negative 20 plus 26, and so that gets us positive 6. Alright, so we are going to have two answers here, and so your polynomial form, all it does is take the f of x and rewrite it. So if we were to rewrite this, it turns out that this piece, which is the result of our division, times this piece, which is the divider, and then plus 6, because that was our remainder, is the polynomial form. Just means what would it equal if we were talking about it being in these factors. Alright, the next one is going to be fraction form, and all that's doing is saying, oh, well, actually, that f of x we had, we divided by x minus 2, and now our result is 3x plus 13, but then don't forget about the remainder, which is 6, but then it has to be over the divisor, so over x minus 2, that thing that we divided. Ultimately, I just want this answer, and so as much as the book will have these both as answers, I'm just looking for this piece, so it's all good. Alright, the next one is synthetic division, and remember that synthetic division only works when you have something that has a leading coefficient of 1 when it's a linear term. So, again, power of 1, coefficient of 1, and then whatever number plus or minus to this. That's the only way it works. So in order to do that, we need to put our intercept right here. Whoops. trying to erase that, our intercept right here. And so notice that I'm not putting the factor, I'm putting the 0 itself, or the x-intercept itself. And then after that, I'm going to put each of the coefficients of each of the pieces. Again, double check that everything has the powers, okay, so no skipping powers. And this k is what we were asking for, which is 3, or that divides there. All right. So then we're going to take each of the leading coefficients. So we have, just each of the coefficients. So 2, -3, -5, and -12. And then we go through and we don't have to think about the powers anymore. So the first step is to bring the first number down. And then the next step is to take that 2 and multiply by 3. And if we do 2 times 3, it turns out we're going to get 6. And so the result of that 2 times 3 goes here, and then we actually add them together. So unlike long division, we're actually adding each of these pieces. So if we add -3 and 6, we're going to get 3. And then you're going to multiply now 3 times 3, this number that's out front here. Okay. And so 3 times 3 makes 9. Again, we're going to add -5 and 9 to make 4. And then we're going to do 4 times 3. 4 times 3 is 12. And we're going to add those again. And so we get a remainder of 0. So the interesting piece about this, especially since you can see what we're dividing, is that if we divide a cubed by a power of 1, we're going to end up with a squared. So this is going to be 2x squared plus 3x, the next lower, and then plus 4 as your solution after dividing. All right, so let's see, works. It doesn't say how to write it, and so we're just going to say that this is our solution. All right, then we have the remainder theorem, which is interesting. So basically you're trying to say, will I get a remainder that I'll have to add at the end? So if a polynomial can be divided nice and evenly by x minus k, then the remainder, which is r, is literally just plugging in k. And remember that k is this number that is added or subtracted to the x. All right. So we're going to use the remainder theorem to determine this remainder. So if I actually took this trinomial and divided it by this binomial, would we get a remainder or not? So all I need to do is identify the k value, and the k value is the opposite of what's in the factor. And so it's going to be positive 2. So all I need to do is evaluate f of 2. And so we're going to have 3 times 2 squared plus 7 times 2 minus 20. If we do each piece, we're going to have 12 for this first section plus 14 minus 20. And so f of 2 is going to be, let's see, 26 minus 20, so 6. Which, of course, we just did up here, right? Nope, just happened to have the same answer. Okay. So in that case, use the theorem to determine the remainder. So the remainder is 6. Okay. So if you went through the long division or the synthetic division, you would in fact have to add that remainder of 6 over x minus 2. In case you needed to jump to that. All right. Then we have the factor theorem itself. So again, the previous one was remainder theorem. Now in the factor theorem, a polynomial function f has a factor x minus k if and only if, remembering back to geometry, f of k equals 0. So as we saw in the previous one, it turns out that x minus 2 is not a factor of this because there ends up being a remainder. So if we look at this next piece, they're just trying to ask you, is this a factor of this? Meaning, am I going to get a 0 remainder? What what is it called? The remainder theorem? Yeah. Alright, so if I get 0, this x plus 4 is a factor. If I get anything other than that, then it's not a factor, and we'd maybe try something else. So we're going to use the factor theorem to show that x plus 4 is a factor, which means it will be 0 in our end. We identify the k value, and the k value is negative 4. It's the opposite of what's in the factor. And so now all I need to do is find f of negative 4. And so I will plug in negative 4 to this equation and hope that I get 0. For the first set, we're going to get negative 4 squared, which is 16, and then 16 times 3, which is, I believe, 48. Alright, and then we're going to get minus 7 times negative 4, and so minus 28, and then also minus 20 from that last piece. So usually when you're solving, you kind of break it up into what's separated by addition or subtraction. And then it turns out 48 minus 28 minus 20 is in fact 0. And so because this ends up being 0, we have now determined by the factor theorem, so we're calling it, factor theorem. It's just that the factor theorem is technically the remainder theorem. Is a factor of 3x squared plus 7x minus 20. Just a statement there. All right, then the next piece that we have, and again, not a fun part of Algebra 2 because it gives you a lot of work to do, but at the same time, it then gives you the answer. So either way, we're going to find the rational zeros. So moving on. Let's see, finding the rational zeros. If we want to find the rational zeros of this, what we get to do is take the leading coefficient, which is 3, and the constant coefficient, which is negative 2, so these guys. And the rational roots theorem says that if you take that negative 2 and find all of its factors and list them out, and then that 3 and find all of its factors and list them out, then these get to be your options. So hopefully you remember this from last year. But again, to save on space, we did not take the time to write 1, negative 1, 2, negative 2 for the numerator, and then 1, negative 1, 3, negative 3. That's what this plus or minus thing is referring to. So either way, you're supposed to do all of these combinations. So for instance, 1 over 1, that's represented here. 1 over negative 1, also represented here. 1 over 3, represented here. And 1 over negative 3, also here. So you just take each one of these numbers and put them over the denominator. And then, of course, you get your pluses and minuses. So all we get to do then is plug in, as we just did in our remainder theorem. If you plug in each of these number options to the original equation and you get a 0 back out, you have now found out that that is actually a factor. So, for example, if I take the number 1 and plug it into the equation and get a 0, I can then say that x minus 1 would be a factor. So if that happened, then that would be a factor. So this is the one that does end up taking a while, but again, if you go with the fact that there are infinite options, and then you actually go here and realize there's technically only 8 options, 8 trials of plugging in numbers is a lot better than infinite. So that's what we're going for here. I will do, of course, the one through on the assignment, but again, you're just looking to see if you plug in each of these numbers, plus 1, negative 1, plus 2, negative 2, and so on, if you get a 0, because then it will be a factor. And of course, since it's a power of 3, that means that there are going to be 3 of them that work. All right, so here's your assignment, and of course, I will be going through each of those problems on our next video.